This one's a bit tricksy. It's about rates. I think it causes a few problems. A rate in science just means how many times something happens in a certain amount of time. Now, to give you an example of this that you'd be familiar with, we might talk about heart rates. So your heart beats, let's say, 70 times a minute. So we might talk about 70 beats per minute. Now that's a rate because it's how many times something happens, 70, in a certain amount of time in a minute. Okay, 70 beats per minute. Now remember that we can write per like this as a slash, because when we do things like meters per second, okay, which actually means meters divided by seconds. Okay, so we could, I suppose, write 70 beats per minute like this. We could write 70 beats per minute. Okay, and that'll become important to us later on. Now, we could have all kinds of things. We could have beats per second, for example. It'd be a lot smaller. We could have beats per hour or per year. We tend to select a time that is most appropriate to what it is we're going to measure. So although we can have things, you might look at how fast a plant grows per year. That might be a more appropriate one than looking at growth per minute, for example. So we can change this. This time constant doesn't matter. Now, the time that, a couple of times you'll come across it, one of the familiar ones is with enzymes. Now, with enzymes, we might talk about the rate of the reaction. The problem with trying to work out the rate of reaction, in other words, how quickly something is happening, is it's very difficult in an enzyme-controlled reaction to see what's going on at the level of the enzyme. So there's our enzyme, I don't know, here's a substrate. We can't look at every individual enzyme and see how quickly it's colliding, or how quickly the substrate perhaps is being used up. You can do it, it's quite difficult to measure these things. So often what we do with enzymes is we measure something like, we measure the product. So if I give, this is hydrogen peroxide, H2O2, which is broken down by the enzyme catalase. Remember, with enzymes we write the name on top of the arrow because it's not used up in the reaction, and it's broken down into water and oxygen. Okay. Now the products in this reaction are water and oxygen. What we usually do in this reaction is we measure how much oxygen is made, and we can count that. We can collect it in a, you have done this experiment anyway, where you collect bubbles of water, bubbles of oxygen going into a jar full of water, and if we let that run until there are no more bubbles of oxygen coming out, we could say that reaction is ended. So we could say, for example, that reaction for a certain amount of hydrogen peroxide, let's say it takes 25 seconds. So we could say that it is one reaction, one entire reaction for those enzymes in 25 seconds. Okay. So suppose it's like saying, scrub that, one whole reaction of all those enzymes and substrate takes 20. So let's extend this a bit. Imagine we did a practical with this. We changed. Oops. We did this experiment at different temperatures, maybe 0, 20, 40, 60, 80, and we measured how long it took to complete the reaction. So perhaps it was taking, I don't know, let's make some up, 45, 25, 10, 70, and then we didn't get any reaction there because it had been denatured. Okay, so classic sort of normal bit of experiment we'd get there. Now if we plotted this, and we plotted temperature against time for the reaction, okay, temperature, remember, is on the bottom, our independent variable, we'd get something like this. It would start off, and it would start getting lower and lower, and it'd go right up, and then we didn't get a value for the end. So we'd get something maybe a bit like this shape. Oops. With a better line of best fit perhaps. Now you might be thinking, hang on, when we see diagrams or pictures of these graphs, we usually get something like this. What we'd expect to see is that kind of shape, where you'd say, yep, there's the optimal temperature at the top, the one it works best at, whatever it is, 40 degrees. Why is this one this shape? Well, it's because this one is plotted as a rate. And remember when I said that a rate, you could think of it like the divide, something per second or whatever it may be. The way you would work this rate out is you would say 1 divided by the time it took. What's the 1 for? Well, the 1 is like saying how long does it take for one of these reactions to happen. So if we went through all of these values, and I'll calculate them all just to show it will actually work. So if we did 1 divided by 45, we get this value of 0.02, and if then I do 1 divided by 25, 0.04, which is higher. Hopefully you can work this one out in your head, but 0 divided by 10, 0.1, which is obviously higher. And this time we will get this graph that goes the other direction. We will get this classic rate of reaction graph. So when you're asked to work out rates, remember it's how many times something happens in a certain amount of time.